Hello viewers, you're welcome to yet another edition of OS e-learning platform, and today we have a discussion on principal mathematics, that is for senior 5 term 1. To all scholars of mathematics, those who are taking mathematics as one of the subjects in their combinations in A level, please, it is high time we share something. And before we continue, let's first thank God for the gift of life. Father in heaven, we thank you for loving us. We thank you for giving us another chance to live and explore our talents. Father, give us the grace to understand you, and give us the wisdom, knowledge, and understanding to explore this mathematics. Thank you, Father, for you've blessed us. All this we pray, believing through the mighty name of Jesus, the Son who lives and reigns within the Holy Spirit, one God forever and ever. Amen. And to Muslims, we pray believing through his mighty name, Allah. You're welcome. And today we shall have the fourth topic of term 1, partial fractions. Partial fractions. Partial fraction is divided into 4 cases, and we shall explore all the 4 cases with the vivid examples, worked out scenarios, and some activities for you to try, and also some scenarios for you to try out. Otherwise, let's get into it. So the competency is the learner decomposes rational expressions into partial fractions, useful in integral calculus and real-world context. So the learning outcomes, actually we have only one learning outcome here. The learner should be able to particularly decompose proper and improper fractions into partial fractions for further learning. So keeping at hand the knowledge, K, the skills, S, the U, understanding, the V values / A, attitude, and then the generic skills. Now, for you to accommodate this knowledge of decomposing proper and improper fractions into partial fractions, you actually need to possess some credentials, and I call them the requirements for the learning outcome. Part 1, express the sum of simple fractions as a single fraction. Express Roman 1 proper algebraic fractions as a sum of simple fractions. And then Roman 2, improper algebraic fractions as a quotient and proper algebraic fraction. So those are the requirements for a learner to achieve the learning outcome. Decompose proper and improper fractions into partial fractions for further learning. Algebraic fractions. So earlier on in algebra, we've been simplifying expressions such as splitted of 1 over x minus 2 minus 1 over x plus 3. And when we reduce this, we come up to 5 over x squared plus x minus 6, whereby we actually get to the LCM, work it out, then we get to this single fraction. So in this topic, we shall make use of the reverse process. Instead, we shall move from this singular fraction to splitted fractions. So we shall move in a reverse aspect of it. However, we have to follow very many rules. Not every algebraic fraction is handled the same way. So they have different cases, and we shall explore all of them in this tutorial. For example, if you are given an algebraic fraction of this caliber, 2 over x squared minus 1, whose denominator factorizes. Otherwise, when you look at the denominator x squared minus 1, you can get a difference of two squares there, whereby one bracket is a plus and the other bracket is a minus. So we may split this to come up to a composite fraction, which is a 1 over x minus 1, then minus 1 over x plus 1. It is now said to be partial fraction. So let's now see how we can add the splitted fractions to come up with a single fraction. So express the following partial fractions as single fractions. So if you look at these fractions, we have 3 over x minus 1 and 2 over x plus 3. At this level, we shall actually get the lowest common multiple. In other words, the LCM, and that will be x minus 1 into x plus 3. And then the next one also, we shall look at the lowest common multiple there, the third and the fourth, fifth, and then the sixth is also there. So we shall try all of them in this tutorial. So the expected responses for each scenario above. So for 3 over x minus 1 plus 2 over x plus 3, I actually need to obtain the LCM by multiplying the denominators. And that will eventually give me 5x plus 7 into x minus 1 times into x plus 3. So the second one, the same thing. Look at the lowest common multiple, multiply the denominators, and simplify everything. You get that final answer. So the third, the same story. Look at the lowest common, multiply, treat individual, just like you are treating fractions. I have maybe plus 1 over 4. So just like you're treating fractions. So here the lowest common multiple is actually 4. Then when I get 4 divided by 2, that will be a 2 times 1 times this one, I get a 2, minus 4 divided by a 4, I get 1 times this one up, I get a 1. So my final answer will be a quarter. So just like you're treating those fractions, it remains the same. Next, if I had 1 over 3 minus 1 over 2, still I look at the lowest common multiple here, and that is a product of 3 and 2, and that will give me 6. So when I get a 6, I simplify everything, I get the answer. So we just look at the mathematics of senior 1 here and look at the fractions, treat them accordingly. Okay. So the next example, and that will give us the final response for that very number 3. Number 4, the same story. You need to be patient, and eventually we shall have our final answers. 5x plus 6 into x plus 2 into x plus 1. So this will be our answer. So this will be our answer if you follow the mathematics there. Be careful, follow all these steps until you get to the answer. Why are we using equivalent? Why are we using equivalent? Is we are getting an equivalent fraction that correlates the original fraction. So we shall use more of equivalent here as we try to express these fractions into single and also vice versa. So the same story here, it is just your patience. You look at this mathematics, follow everything, you'll get that answer. I think I will concentrate on number 6. Now number 6, they want us to make it a single fraction, and by the end of the week we solve for x, in that that very single fraction is equal to x over 5 minus x. So what we shall do is still get the lowest common multiple, simplify that. So the simplified fraction is actually 17x plus 139 over 5x plus 35. So it is this single fraction that we shall equate. It is this very single fraction that we shall equate to what is given as a representative of the original splitted fraction. So what we shall have is 17x plus 139 over 5x plus 35 being equal to 8 over 5 minus x. And that will give us a way forward on how to solve that very value of x. So we equate now in the next level. Can collect like terms such that the right hand side remains with a 0. Simplify, get the lowest common multiple by multiplying the denominators. Simplify everything. You come up with a quadratic equation whose constant a is negative 17, constant b is negative 94, and constant c is 415. So we shall use any method, and for this I decided to use general method, and ultimately the respective values of x are 2.9 approximately, because I rounded off, and that is 2.90 and negative 8.43. You can treat it and put it to 4 decimal places just to increase the level of accuracy. So this is your activity. You can pause the video and you go through them. And please, if you want to confirm the response, prepare your small money and buy this book, Mathematics A-Level by OPERO Stephen. Prepare that money and you own yourself a textbook of A-Level containing all the math you need. Try those items, try those activities to just check the level of knowledge you've acquired so far. Well, partial fractions. Now, basically, this is the gist of the matter, and I want us to dwell on the 4 different types of algebraic fractions, and we need to learn how to express them into partial fractions. In this scope, we shall actually do the reverse. We've been adding 2, 3 splitted fractions to come up with a single fraction, and we want to check now, is it possible to actually do the reverse of it, whereby now I move from the single fraction I have back to the splitted fractions. The question is it possible? And the answer is yes. However, you have to respect the 4 different cases. Allow me to summarize them. The first one is when you have a linear factor as a denominator. In that single fraction, you will have a factor as a denominator. These factors can be the same or different as long as they are linear factors. And if it is a linear factor, one factor, each linear factor takes a different form of a partial fraction or a splitted fraction. Now for these linear factors, we can have linear factors that result into a quadratic equation, meaning sometimes instead of giving you linear factors, they give you a quadratic equation, but that equation has linear factors, can be factorized. So you should remember that each linear factor takes a certain caliber of splitted fraction, algebraic fraction. Case 2, when the linear factor, actually when the quadratic equation does not give linear factors, when the quadratic equation given as a denominator gives what we call no real roots. For this case, that very quadratic equation will take a different caliber of partial fraction. And mind you, we mix them sometimes. You can get two fractions. I mean one fraction but having two denominators, and of which one denominator is actually a linear factor and another denominator is a quadratic equation, but that quadratic equation has no factors. So you should respect that case where the quadratic equation has no factors. Next, when we have repeated factors, for example, when you solve a quadratic equation and you get repeated factors. And why am I explaining all this here to the first presentation about quadratic equations? We talked about all this. So you should just remember that, okay, for this case now, I have repeated factors. For example, x minus 1 everything squared. That is a repeated factor. These are cases where you solve a quadratic equation. It gives you the same value for x twice. Check here. The last one is when we have improper fraction. An improper fraction is a fraction where the algebraic function in the numerator, the power of the algebraic fraction, or the highest power of algebraic fraction, is actually greater than the highest power of algebraic fraction, algebraic expression in the denominator. So that one is a case where we have an improper fraction, algebraic fraction. For that case, we shall make use of long division. So basically, there are 4 cases, and in each case, I will give you one example, one scenario-based item worked out, and I will subject you to trial activities. And if you need scenarios, please prepare your money and buy the textbook. All the scenarios are there. Next, we shall close the chapter with the importance of partial fractions. So we must check whether the values obtained are true by either 1. Getting the lowest common multiple to get back to original fraction, or substituting any value on both sides of the equation. So these two are methods of checking the validity of our expressions. You see, sometimes we solve this and get the splitted fractions of the single fraction, and at some point we do not actually leave the house comfortably because we think at some point our answers are wrong, our responses are wrong. Now, to leave the house while you're very comfortable and confident, you have to first check whether the left hand side is equal to the right hand side by substituting any value as the value of x. Why am I using x? In most cases we play with expressions in terms of x. However, if it is in terms of t, p, q, do the same thing. The same way we treat x, it is the same way we treat p, r, k, etc. And another thing, you can look at the LCM. You can do now the reverse. Remember, here we are splitting a single fraction, algebraic fraction, into partial fractions. And then, if you want to confirm, you can take the reverse now. From the splitted, take the LCM. Actually, you do what we have just done in the previous slide. Case 1, denominator with linear factors. So each linear factor of this caliber, ax plus b, in the denominator has a corresponding partial fraction of k over ax plus b, where a, b, and k are constants. Example, partialize or split or decompose the following. I have this one example for you. 5x plus 7 into x squared plus 2x minus 3. If you remember very well, this is one of the examples we have in the previous slide, where we had some 2 fractions, algebraic fractions. We subtracted them, simplified them, and we came up to 5x plus 7 over x squared plus 2x minus 3. So in this, we are going now to take the reverse. We need to get the splitted fractions of this single fraction. So the expected response for this, now if you look at this expression, well, it is a quadratic equation that has factors, and these factors are linear. So this is what I was meaning, that at some point we shall have a quadratic equation of this caliber, and at this point we should be in position always to look at a quadratic equation and realize this one has two distinct real factors, and these factors are now linear. So when you have these linear factors, then we are going to take a case where each denominator takes a fraction of the caliber a over ax plus k over ax plus b, and then after k we go to another letter. So we prefer capital A, capital B, capital C, etc. So we check on how we are going to do this. So we are splitting each denominator into a over x minus 1 plus into plus b into x plus b over x plus 3. So here I still take the lowest common multiple by multiplying the denominators, simplify everything, I get something similar to that. So you can see that the denominators are the same. So if I multiply both sides by the denominator, I actually remain with 5x plus 7 is equal to a into x plus 3 plus b into x minus 1. Now from this point, I really want to get the value of a and b, such that I get back to my expression, this, then I just substitute for a and b. So by the end of the day, I will have splitted this original function into partial fractions. So I need to solve for a and b. There are two methods. I will give both of them here, and in the subsequent examples, activities, we will decide the one you prefer. So the first method here, I will solve for a and b. I use the first method. In the first method, my target here is to make sure one part of the right hand side collapses. How can I diminish the one side? For this, for example, if I want to diminish this part, I plug in x as 1. When I get to 1 minus 1 here, the whole of it will be a 0, and the 0 times b, all this will collapse. That very one, I come here also, I substitute 1 plus 3, the whole of this will be 4. And then here I will be having 4a, yes. And then here I put 1, I plug in 1, so this will be 5 times 1, which is 5 plus 7. So the whole thing will be, the left hand side will have a 12, and the right hand side will have a 4a. So the same thing, this will help me to find a, and my a will be equal to a 3. And the other case also, if my target is to make this part collapse or diminish, I will set a value that makes this fraction, this bracket, become a 0. And for that, the value is negative 3. So this a will collapse, and here I will remain with 2b. And on the left hand side, I will remain with the 15 plus 7, something like 22. So basically, we need to look for all ways of solving for a and b, such that we get back to the splitted fractions and substitute the respective values of a and b. So if I plug in that, of course, in the left hand side I will have negative 8, and the right hand side I will have negative 4b, and by the end of the week my b will be equal to 2. When I plug in x is equal to 1, left hand side I will have 12, and the right hand side I will have 4a, and ultimately my a will be equal to 3. So now that I have a and b, I can get back to my splitted fraction and I just substitute, and that will give me the partial fractions of the single fraction at hand. So therefore, the single fraction will be equal to 3 over x minus 1 plus 2 over x plus 3. So basically, if you want to confirm, you can take this back to its single fraction by looking at the LCM. Actually, the first presentation on this the first, second, or third slide on this very presentation. So you can take it back and confirm, or you can pick any value of x. For example, if my x is equal to 1, you can pick any value. Substitute here 1, simplify this right hand side, carry that very 1, substitute on the left hand side. You will ultimately get the same answer on both sides. So that one vividly shows that your answer is actually correct. The splitted fractions, the decomposed fractions are actually correct. That is how we can prove. Method 2. This second method is all about opening this bracket and comparing the coefficients of the individual terms. Now when I compare the variables on both sides, I get to realize that I have terms where I have constants. On the left hand side, the constant is only 7. And on the right hand side, the constant is actually negative b plus 3a. Those are the constants I have. I have this negative b, I have negative b as my constant here, plus 3a. Those are the constants. So if I equate them, I come up with an equation. Another thing, I have the coefficients of x. The coefficients of x, we have this part where we have 5 as a coefficient, and on the right hand side I have ax and bx. So I have to compare them, and by the end of the day my 5 will be equal to a plus b. So those two equations, I solve them simultaneously, I actually get the values of x. So let's get those. If you look at the constants, on the left is equal to constant on the right. 7 is equal to 3a minus b, and that is equation 1. Coefficients of x, on the left hand side I have 5, right hand side I have a plus b. Solving the two equations, I get the value of a as 3 and b as 2. Simplifying back to, or plugging back to my original partial fraction, I actually have to plug it back here. Where a is, I put a 3, and where b is, I put a 2. So that will be a splitted part. So you can see that even the second method gives us the same thing. Now, it is unfortunate that our example ends on x power 1. In other examples, when you're using this method, you'll get where we have the left hand side having variables of x power 3, have x power 2, etc. So you just compare the same. For that case, we shall still look at the coefficients of x power 3 on the left hand side and also on the right hand side. The same thing with the coefficient of x power 2 on the left hand side equal to coefficients of x power 2 on the right hand side. After opening the bracket, and while opening the bracket, you need to be very, very present. You need to be very sober, and make sure as you're collecting those coefficients, don't forget any term. If you leave any term, you'll not get the correct response. So basically, it is upon you now to choose which method to use, but me, I prefer the first one because it's very, very easy for me to use. So after learning something from the previous slide, can you please try out these activities? So decompose the following algebraic fractions. Here we are meaning split, partialize, express them into partial fractions. So that's why we are using decomposing. Decompose. So examples are there. As you can see, their denominators are actually linear factors. Even if you get a quadratic equation, try to check whether it is a linear factor. Like example 5, that is a difference of two squares. You should be in position to always look at something similar to that and be like, okay, this is a difference of two squares. One bracket is a plus, the other bracket is a minus. So be careful, all of them are linear factors. Even number 10 is a difference of two squares. The denominator, I mean. And if you want a response, please check in the book. Own a book, please, and see how you can maneuver this advanced mathematics. So let's try one sample item. Nasozi, an economist at a certain commercial bank in Uganda, is evaluating the financial feasibility of a new infrastructure project. As part of her cost-benefit analysis, she encounters a complex cost function that models how costs vary with a key parameter x, such as production level or interest rate changes. The cost function is given by the following rational expression, as you can see. So my interest is that you examine that denominator. If you look at the denominator very well, we actually have a linear factor and a quadratic equation. But this quadratic equation has linear factors. So basically, these are three linear factors that you should keep in your mind and get to know, okay, each linear factor takes a particular case of splitted fraction. Stakeholders are concerned about the potential rise in costs, and NASO's needs to present a clear and simplified breakdown of the expression to interpret its behavior more easily and evaluate whether the project is financially viable. Task: using the knowledge of principal mathematics, help to interpret whether the project is financially viable. So what we need here is to decompose this single fraction that is quite complex and complicated into splitted or partial fractions. Then we go on each partial fraction, explain its significance in terms of its sign. If it is a negative, it implies a reduction. And if it is a positive, it implies an addition or an increase. So for that case, in terms of cost, what will a negative mean and what will a positive mean? So let's look at the expected responses. Here we have to decompose the cost function into simple form for easy interpretation. So if you let our cost function be y, and that will be equal to the original function given, where y is the cost function, I will still let my cost function given take individual partial fraction. And as you can see, x squared minus x minus 12 gives me factors that are actually linear, and these factors are x minus 4 and x plus 3. So this is a quadratic equation but has linear factors. And if you want to test before even practicing it, you have to use the other codes I gave you in the presentation about quadratic equations. So for this, on the left hand side, I have a simplified part of a quadratic equation into linear factors, and I have three linear factors. On the right hand side, I have individual fractions for each factor in the denominator. So I will take the lowest common multiple by multiplying all the denominators. I simplify. Please take your time there and simplify. And by the end of the day, since the denominators on both sides are the same, I multiply the denominator on each, and eventually I will remain with the numerators being equal to that. So on simplifying, I want to solve for a, b, and c such that I get back to the original partial fractions. This part here, and then I substitute for a and b, and guess what? By the end of the week, we shall be having our response. So for this, I will set, remember the target is to make sure I kill some variables on the right hand side such that I remain with convenient variables to simplify. So if I set x is equal to -3, are you aware, -2, are you aware that this part will collapse? Because a negative here, -2 plus 2 is at 0. Since multiplication is taking place here, so I will remain with the 0. Even here will be a 0 because a -2 will affect that part. So eventually I will remain with this part and I will get my value of a. So my value of a will be 3. When I plug in x is equal to 4, my target is to kill which part? My target is to kill this part because it has a 4 in, and also that part. So I will remain with a b, and by the end of the day, substituting x in the left hand side and also the right hand side, my b will be equal to 7. Next, when I plug in x is equal to -3, my target is actually to kill that part with a b and that part with an a. So by the end of the week, this part will be gone, and also that one, because a 3 is there, and then this part will remain, and that will give me the value of c. So the left hand side is substituting in x is equal to -3, left hand side I will have -7, right hand side 7c, so my c will actually be -1. So therefore the simplified cost function is where x is, I remain with my x, but where a, b, and c are, I really substitute for their respective values. And by the end of the week, I will, why am I talking about the week? By the end of the slide, I will have my answer expressed in this form. So this is a decomposed part of the original simply complicated algebraic fraction. So if you want to prove, you pick any value of x. Can set my x be equal to maybe 2. When I substitute it here, I will get the answer that is actually similar to when I substitute x is equal to this one. Actually, there's the same. So that one vividly shows you that our partial fraction or decomposed fractions are correct. And then we need to explain the significance of this partial fraction such that we can help nurses to interpret the cost function and to interpret whether the cost function is viable, financial status is viable. So can we interpret? So this simplified form helps nurses identify critical point, what we call the vertical asymptotes. Now, if you try to sketch this function, those who are familiar with curve sketching, there's what we call vertical asymptotes. Ideally, these are values of x that determine the range within which we expect the function to lie, and also the x-intercepts. But basically, the region where we don't expect the function to lie is very, very important, because that's where we don't expect the cost to exist. So at that point, we say the function is undefined, and it is undefined at points when we have x is equal to -2, x is equal to 3, and x is equal to 4. So when you come to these functions, we get to realize that the function is undefined when x is equal to -2, when x is equal to -3, and x is equal to 4. So these values of x should be avoided in the analysis. Trend at large x. So as x tends to positive value, each fraction tends to 0. So the total cost decreases and stabilizes. This suggests cost efficiency improves at higher production. Or favorable interest. Let's look at the case 2, where the denominator has a quadratic factor, and that quadratic factor cannot be factorized. Quadratic expression in the denominator of the given single fraction, algebraic fraction, but that denominator, that is a quadratic denominator, has no factors. So each quadratic factor in that caliber, ax squared plus bx plus c, in the denominator, which is irreducible, in other words, has no factors, will not factorize. And for that case, the corresponding partial fraction is in the form ax plus b over ax squared plus bx plus c. So carry the very quadratic equation, quadratic expression, write it as the denominator, and then the numerator will take a caliber of ax plus b, where a, b, c small, and capital A and capital B are constants. Let's look at this one example. Split that. So if you look at this quadratic expression, probably there is a quadratic expression in there. However, this expression has no factors. It is actually a polynomial of degree 3, but it has no factors. Not really a quadratic, but a polynomial of degree 3 as a denominator has no factors. What are we going to do to get the factors here? This is what we call inspection method. We are going to inspect which value when I substitute on as a value of x, and this denominator becomes 0. That is a value of x that will satisfy this polynomial. Then we shall ultimately use long division and get other factors for this polynomial. So let's look at expected responses. For the first one particularly, if you look at that, yes. Now if I use long division and use x minus 1 as a factor here, I will get the quotient as x squared plus x plus 1. I'll get a quotient of this caliber. So if you want to learn more about long division, be patient. In the next next slides, you will get the presentations talking about long division. So particularly at your free pace, you can still learn, make research on long division, and when you take x minus 1 as a factor for x cubed minus 1, then the quotient will be x squared plus x plus 1. So when I multiply the quotient and the factor, I get back to what we call the polynomial. So basically, since our new single algebraic fraction has a linear factor, and this part here is a quadratic expression, but this quadratic expression has no factors. So the case that is a linear factor will take this case where a over that very factor. Then the case that has a quadratic equation but with no factors, where grade takes the caliber of this splitted fraction, whereby you maintain the quadratic equation as the denominator, and the numerator will be in terms of bx plus c. Why am I using b? Because I've already taken a in the first case. So if I had another maybe linear factor and it is b over that very linear factor, then I would move to cx plus d. Okay, so simplifying everything, I need to solve for a, b, and c. So by plugging, you see, after getting the LHM, it's only the numerators that are equal, and for that case, or equivalent, for that case I will still solve for a, b, and c. I gave you two approaches. If you want, you can open the bracket, compare the terms, the coefficients. And for me, I decided to use plugging in x is equal to 1 such that I eliminate some part. So when I eliminate the right hand side, I will remain with 3a, the left hand side I will remain with 2, so a will be 2 over 3. When I plug in x is equal to 0, I'm targeting b to get cleared, and I solve for c, given that a will remain, but a is 2 over 3. Simplifying everything, my c will be negative a third. Now I need to solve for b, since I have a and c. So I can plug in any small value that can give me an expression, in that when I substitute the values of a and c, they are very, very convenient that I can get the value of b. So in that, I will substitute the values of a and c. So basically, my b will be negative 2 over 3. So therefore, the expression x plus 1 over x cubed minus 1 will be partialized, and the final answer will be 2x plus 1 over 3 will be 2 over 3 into x minus 1 minus. So this is the resultant thing. Please check. And please, this video I'm uploading it once does not mean you will also understand it once. You need to get serious also. So you can go through these videos for about 8 periods, because as per the standard structure from NCDC, you have to go through this for 8 lessons, 8 periods. So I'm uploading it once, then you can go through it in phases. You can just decide today I'm ending here. Remember, the time is allocated there, so you divide your time and be like, okay, if the video is going for 1 hour, then I can go for more 20 minutes or 30 minutes, or even 10 minutes. The most important thing is you to understand. And if you're not understanding something, lay down your comment, I will respond. And basically here, because of time, we can't go very slow that we explain a term per term. We need to simplify life such that we also minimize the resources. Activity for you there, try it. Try to decompose those. The most important thing as you're doing this is to check the denominator. If you look at the denominator here, it is a quadratic expression, but when you solve this in a calc, it will never give you a real root. So what we shall do is, it will take a different case of this very above case, where the denominator is a quadratic expression but has no linear factors. Even this one here, when you solve, it has no linear factors. However, this is a linear factor, so that will take a over b, sorry, a over the other very factor, but this one will move to bx plus c. If you look at this one, still the same story. This part here is a quadratic but has no linear factor, then that's the linear factor. So the linear factor will take its only special case, then the quadratic will also take the case of bx plus c over that very quadratic expression, given that one linear factor is there. If there are 2 linear factors, then a and b will be taken, then we shall shift to c, x plus d as the numerator for what? For that very quadratic expression that has no linear factors. So examples are there. Please take your time, try them out, and find the responses in the book by OPERO Steven. I think we can now try this scenario. Sample item. A team of climate scientists at the Uganda Meteorological Authority is working on a project to model the impact of climate change on Uganda's agriculture. The team has collected data on the climate variables and wants to develop a model to predict the impact of climate change on crop yields. The model involves a rational function. If you look at that function, we have one linear factor and a quadratic expression. This quadratic expression has no factors. I mean the denominator. My dear students, concentrate much on the denominator. Look at the denominator you have. If you look at our denominator, the denominator has a product of 2 expressions. This is a linear factor and this is a quadratic factor. Sorry, a quadratic expression. But this quadratic expression, when you try to solve it, it gives you no real roots. So this one has no linear factors. And please, for that case, you should just remember what we've done in the previous in the previous slide. So every partial fraction task you should concentrate much on the denominators, where x represents time in years and the numerator and denominator represent the climate variables and crop yields respectively. The team wants to develop a more accurate model for predicting the impact of climate, to evaluate the model's performance change, and to make prediction about the impact of climate change. However, the rational function is so complicated to them, they can't interpret, and they need your help. Task: as a student of pure mathematics, help the team. So basically here you need still to decompose the complicated complicated algebraic fraction and decompose it into splitted fractions, and these fractions you look at the signs on each and explain the significance of each. In regards to crop yield, climate variable, which is ultimately the numerator and the denominator of each partial fraction. But basically what I need us to learn here is to decompose partial fractions. That is what you need to know. And then in the further we shall see how we can make application of this. And remember, the crucial or the most important thing with partial fraction is we make use of it while performing integrations. You will be given an integral function. In other words, you're finding the area within which a function lies. But that area you have to integrate an algebraic fraction that is of any caliber, whether it is of a repeated linear, quadratic denominator that has linear function, has no linear function, whether it is of an improper. So it will depend, but mostly I want you to learn how to partialize, how to decompose, how to rationalize. In other words, how to split. So we get to realize that we decompose the rational function to be in position to interpret the climate change, because this single one is complicated. As you can see, our first bracket x plus 2 is a linear factor. Then the second bracket x squared plus x plus 1 is a quadratic equation with enough linear factors. So it will take that caliber. My target's on the numerators. Two methods here. You can open the bracket, compare the coefficients of x squared, x, and constants, and solve those equations simultaneously. Or you can use the other method of setting, such that you kill other parts, you eliminate other parts, and you remain with the part that you can get. It is the value. So when I plug in x equal negative 2, my target is to eliminate that part with bx plus c. Then the left hand side ultimately I will remain with 6. Just plug in, take your time, press the calc and get the correct thing. So on the right hand side I will have 3a and a will negative 2. Plug in x equal to 0. Still I'm eliminating a b, I remain with a c and an a. Since a is negative 2, so I plug in. The left hand side gives me ultimately 3, and this is not a 3, it's a negative 2. Yes, the left hand side, when I plug in x is equal to 1, the left hand side will give me left hand side I will remain with a 3, then the right hand side will be a 3. Then when I plug in x is equal to 0, the left hand side I will mean with a negative 2, and the right hand side I will mean with a plus 2c. But my a is a negative 2. So when I simplify everything, c will be equal to 0. Then when I plug in x is equal to 1 on the left hand side, I will get 1 plus 1. This is a 1 plus that, that is a 5. 5 minus 2 is a 3. So the left hand side will be equal to 3. Then the right hand side I will have an expression of that caliber. Since I have a and c, I can still substitute and get the values of, so I get the value of b, which is equal to 3. So my a is negative 2, b is 3, and c is equal to 0. So I substitute them back to the original function that I have, which will be ultimately a is negative 2, b is 3, and c is 0. So by the end of the day, this will disappear and it will go to the village, and that will give me 3x over the quadratic expression that has no linear factor minus 2 over x plus 2. Now if you look at this part is a positive and this part is a negative. So a negative means a reduction and a positive means an increase. So we need to interpret this as far as the climatical change and crop yield are concerned. So let's look at the interpretations of this very part very fast because of time. So the decomposed part is that overall interpretation. The model predicts that early alone crop yields may be negatively impacted because of this negative part, because there will be a reduction in the output. However, as time progresses, the impact becomes more positive and stable for the positive part of the partial fraction. That will be dominated by the part 3x into x squared plus x plus 1 term. So this one is an increase with the time and a negative reduction. So this suggests that the initial shocks from climate change may cause yield drops, but adaptive measures or stabilizing factors could improve outcomes over time. So basically, what I need you to keep in your mind, this will sound a bit complicated to explain, but just know that that part with the negative implies a reduction. If it is production, reduction. If it is sales, reduction. If it is yields, reduction. Then positive, you have to connect it to the scenario. Basically, that is my analysis as a professional teacher of mathematics. So after analyzing all this, how do we use this? Now, practical use of for the team. 1, help identify critical years where intervention is crucial. Now, we look at the periods when the function is nullified. When we have x equal to negative 2, x is equal to negative 2, take only one x is equal to negative 2. This is a repetition. At this level, just pick one. All this is not there. Just remove it. So at a point when we have x equal to negative 2, actually this part will vanish. So we should do away with periods when x is equal to negative 2, and intervention should take place there. Enables simulation and forecasting under different scenarios of time and intervention. Can also make policies, timing, and also suggesting more effort on to improve on the impacts of these seasons. So basically that is what we should know. But one thing I want you to master is how to partialize, how to decompose partial fractions. Basically that. Then as we digest many questions, let's look at the other second last case where the denominator is with a repeated factor. So each repeated factor, of course these factors are linear, will take a form of that, a over ax plus b over ax plus b, but squared, because it is moving up to squared. If it is cubed, it goes to c over a plus b cubed, where a, b small and a, b capitals are constants. Can we try this example? The examples are there. If you look at example 1, our denominator, I told you concentrate on the denominator. The denominator, we have a linear factor, single, and this linear factor, but it is repeated. It's like times x minus 1 again. Here it is a linear factor, but again here it has a repeated factor. Actually, this factor, linear factor, is repeated 3 times. Here it is a quadratic expression with no roots, with no linear roots or factors. And then it is a linear factor, but it is repeated linear factor. In other words, when you open this, you get a quadratic equation, but this quadratic equation has repeated roots. So the question is, how do we treat something of that caliber? How do we treat expressions of this type? So let's look at the first example. We agreed that the first linear factor will just take that case of a into x plus 1. Then, since these are linear factors, they will take a over that, b over that, c over that. But now this one that is repeated, we take it up to the highest power of the it is repetition. For example, x minus 1, it is repeating twice. So I will take it for the first case and also for the case when it is 2. And then if it is 3, I will take it the first, second, and for the third. So I keep just increasing the power up to when I get to the last power in the question at hand. Still, the concept remains the same. Look at the lowest common multiple by multiplying the denominators. But if you look at this, these are repeated factors. So I will take the highest factor with this x plus 1. So that's why I will have x plus 1 into x minus 1. Everything for that is squared. Then I look at the LCM. My target is to compare the numerators. When I plug in x is equal to 1, left hand side must be equal to right hand side, and my c will be equal to 1. Plug in x equal to negative 1. Please now at this point should be knowing what we are doing. My a is a half. Plug in x is equal to 2. Ultimately, I get some equation whereby I plug in the values of a and b, and then I will get my, a and c, then I plug in values of x and a and c, then my b will be negative a half. So ultimately, the fraction I have decomposed will be equal to that, where we have a fraction of this caliber now. So this is a splitted, and it's now easier to interpret this. And if you want to confirm, set value of x, any value of x, put it here. Maybe it is 2, put it there. Even this side also, carry that very value you've decided to plug in. You substitute and you see whether you get the same answer as per the right hand side. So that's how we can prove that. And basically what I need you to master is, how can I treat a case where we have repeated factors in the numerator and the denominator. So a scenario for us to try is here. You are among the team of demographers at the Bureau of Statistics working on a project to model population growth in a country. The team has collected data on the population size and wants to develop a model to predict the future population trends. The population growth rate is given by, population growth rate is equal to that. If you look at this case, we have one linear factor and a repeated factor, but this factor is, linear factor is repeated 3 times, where x represents time in years. The team wants to understand how the population growth rate changes over time to inform population growth projections. And your role in the department is to develop an algebraic fraction to represent the population growth rate, decompose the algebraic fraction using an appropriate method, write a report on the results, including any conclusions drawn about the model's performance, and suggest for future work. So my task here is you to know how to write this algebraic fraction, decompose it, basically decomposing it. So the task showcases the layout of your report as a student of principal mathematics. So here I'm still decomposing. As we are decomposing, we need to look at the case. Which case is this? We have a linear factor and another linear factor, but this linear factor is repeated 3 times. So it will take that case where we have, as you can see, the first factor is a over x plus 1. Second is repeated 3 times. So I move up to the third case where a, since a is taken, I go to b, c, and d. So by the end of the day, take the LCM, play with it. Play with it, please. At this level, this is advanced math now. You need to be in position now to simplify. If you look at this, the common multiple is actually picking this x plus 1 and this one of the highest power. Because all of them, you can see this is x minus 2, x minus 2, this is also x minus 2. Now what we shall do is to take the one with the high. So I multiply this with that to take the LCM. So that's why I'm taking it here. So I consider that, then I divide on each case as I multiply with the numerator. I divide on each case as I multiply the result with the numerator. I divide, keep adding. I divide with this as I multiply the result with the numerator. What am I dividing? I'm dividing this LCM. So I do the same, then that's why you get this numerator. So now the numerator will be equal to the other numerator on the left hand side. So basically that is what we should do. So on plugging, I get my a as negative 2 over 27. Plugging x equal to 2, I get my d as 5 over 3. Plugging in x equal to 1, I get my, solving everything, I get my, what are you talking about? I get a simultaneous equation, or an equation with two unknowns, that is 8 is equal to 27b minus 27c. Check here. Plugging in x is equal to 0, I still get my second quadratic equation. A second linear equation. And this linear equation is 26 is equal to 54b minus 27c. Then here I have this one also. So I have to solve this simultaneously, and guess what? We shall have our b as 2 over 27 and c as negative 2 over 9. So I substitute these values back to this splitted or decomposed fractions, and by the end of the day I will have my fraction there. And if you want to prove, set x any value, solve. So interpretation: the partial fractions reveal how different time-based components affect population growth. The term x minus 2 becomes dominant near x equal to 2. In other words, the term x minus 2 becomes a 0 when x is equal to 2, indicating the population tipping point or population shock. The model shows that growth is not linear but influenced by a combination of short-term factors, etc. Anyway, basically that is what we need to know, but don't harden life with the explanations. First master how to decompose. Then in more scenarios, as scholars are generating more scenarios, we shall come to a conclusion on what we should actually elaborate as far as the interpretations are concerned. So these are your activities, please try them out. These are your activities. Look at the denominator. Last case is improper fractions. Here we are going to make use of long division. Be patient, please. So as you go through that literature, in summary, the highest power of the variable in the numerator must be greater than the highest power of the expression in the denominator. And for that case, we do what we call long division. We divide the numerator by the denominator such that we can get a simplified expression. So when a polynomial of degree n is divided by a polynomial of also of a degree m, the quotient is a constant. Check here, this should be n, because if you get a polynomial of degree n divided by a polynomial of also degree n, this should be n. Like when you have a polynomial of x squared and also down is x squared, so when you divide them, you get a constant value. So when a polynomial of degree n is divided by a polynomial of degree m, where m is greater than n, then the quotient is a polynomial. Okay. We can also use long division. Basically, this is what I want. We can division. So let's look at the sample scenario. The Ministry of Energy in Uganda is conducting a study to model and predict the nation's energy consumption trends over time. Energy analysts have developed a mathematical model to represent energy demand using the following rational function. Look at the denominator. Denominator, if you open the denominator, its highest power is 2. The power of x is 2. Then the numerator, the highest power of x is 3. So for this case, we shall do what we call long division. So it is a case where we have an improper algebraic fraction. X represents the time in years. The numerator represents contributing factors to energy demand. And then the denominator represents supply side constraints. Task. You are part of the analysts. You are part of analysis team to assist in interpreting energy trend and forecasting future demand. Decompose the algebraic function. This is very simple. You don't need to explain, you just need to do this. So the expected response here, after realizing that the thing is of an improper case, improper algebraic fraction, I have to expand the denominator, and you can see that the highest power of x in the numerator is actually 3, and the highest power of x in the denominator is 2. So here I will perform what we call the long division. Degree of a numerator is 3, degree of the denominator is 2. Since the numerator has a higher degree, we must first perform polynomial long division before partial fraction decomposition. So the next step is polynomial long division. I will write my what I'm dividing, the polynomial I'm dividing. X cubed plus 2x squared minus 2x plus 2. Divide it by x squared plus 2x minus 3. So I get my x cubed divided by x squared, I get my x. When I multiply x times x squared, I get my x cubed plus 2x squared minus 3x. So when I subtract this, I get something of that caliber, x plus 2. Because all this will be a 0, all this will be a 0, all this will be a 0, and this will be negative 2x. Negative 2x minus this minus here, then minus again, it is a minus 3x, so minus 3 x. So this one becomes a positive. Remember here is a x, so it's like 3 minus 2x. 3x minus 2x, I get here x. And remember here it's like having a plus 0. Plus 0. So if I get 2 minus 0, I get my 2. So this one here is what we call a quotient. It is a quotient. Quotient in terms of x. This one here is the one we call the divisor. The divisor in terms of x. Then this one here is one we call the remainder in terms of x. Actually, I will upload the other video about polynomials, and you will help me now go through that work, because it will be now very easy. And that is what we call a polynomial. Polynomial, we are dividing polynomial of x. Now all this comes from P1 mathematics. P1 mathematics, if you remember that P1 mathematics, I want us to recall something here. Remember this. If you remember the primary mathematics, if remember this very well, at some point we're given 5 divided by 3. Remember, this is quite complicated at P1 level. Then you'll be like, let me use my long division. I get 5 divided by 3. When I get 5 divided by 3, I get 1. Because 3 goes into 5 once. Then I have some remainder. So I need to get that remainder. So I get my 1 times 3. And when I get 1 times 3, just let me see this. When I get 1 times 3, when I get 1 times 3 here, I will get 3. Then I have to subtract. So 5 minus 3, I get 2. So when I subtract. So this one is the quotient, this is the divisor, this is the polynomial, and this is the remainder. So the remainder is that. So how can I write that? 5 divided by 3, it's like having one whole number, 2 over 3. One whole number, 2 over 3. So that's how I need to write also this algebraic fraction. So polynomial of x is equal to quotient of x plus remainder of into x over divisor of or into x. So this one here, this one vividly shows that if I decide to multiply both sides by divisor, you get to realize that the polynomial times the divisor is equal to quotient plus remainder. So I can still play with this in any other way. So what I will do is to express this original function in terms of quotient into x plus remainder of x divided by divisor into x, I will get something of that caliber. Because when I try to simplify this, right hand side, I still go back to this by getting the LCM, simplifying everything. So the definition of remainder theorem or polynomial theorem will help us here. So this is very important. So you just need to identify what is my divisor. Divisor is that one. What is my remainder? My remainder is that. I will write it where it is required. So the divisor, I will write it there. The quotient, I will write it here. And then the remainder, I will write it here. Okay. So perform long division very well. And where do we end on the remainder? We end when you can't divide anymore. So that basically gives us the third part of decomposing now. You get to realize that in this part we have to decompose now the ratio of the remainder to denominator, because it's the one that is still having a single fraction that has a quadratic expression, and I think this quadratic expression has factors, that is x minus 1 and x plus 3. So simplifying everything, looking at the numerator, I plug in x equal to 1, my a is 3 over 4. Plug in x equal to negative 3, my b will be equal to 1 over 4. And guess what? My final response, that is the decomposed form, will be as simple as that. That will be the response. So since they want me to just decompose, this will be the final thing. So the final response or decomposed. So these are your activities. Try them out. Yes, try them out, please. Try them out to check your level. So uses of partial fraction. We are going to make use of this in integration. We are going to use them in integration, as you can see that example. For us to integrate that easily, we need to express into partial fraction. We are going to use this under solving differential equations. We are going to use the inverse Laplace transformation. This is at the university. And also in the Department of Engineering, we make use of that. Simplifying algebraic expressions, of course, we have done that one. Control systems and signal processing, engineering still, etc. in complex analysis at the university. So basically at our level, we shall make use of number 1, yes, number 2, and also number 4. The rest is when you go to the university. Otherwise, thank you so much for your contribution. Thank you so much for your time, and allow me pause here. Don't forget to like, subscribe, and why not? End here. Thank you so much.